So a very good evening to everyone. So I am Sahil Gaurav, PMRFTA for this NPTEL course, Design of Photovoltaic course, Photovoltaic Systems. And currently I am doing PhD at IIT Guwahati under the guidance of Dr. Chandan Kumar. I am doing research on control of power converters for a smart transformer in distribution system. So what I am going to do in this live tutorial session, we are going to discuss the similar type of problems that you have to solve in the current assignment. And you have to just see the process. And if you face any doubt, any problem, you can ask me or interrupt me. And you also need to do that. You need to just take your paper and pen out. And when I am solving, at that time, you need to also parallelly solve the same problem. And you can give the answer in the chat box, or you can tell the answer also. You can speak also. So let us begin this first live tutorial session for this NPTEL course, Design of Photovoltaic Systems. So before we begin to solve this problem, we have a quick recap that will be helpful in solving this assignment. Like, let us begin with these parameters of photovoltaic cell. So first, starting with short circuit current, if you see the expression that has been derived in the class, that is coming approximately equal to the photocurrent. And we know that this photocurrent is directly proportional to insolation, that is incident solar power. So that means you can tell that short circuit currents ISC varies linearly with the incident solar power of insulation or solar insulation. And the second parameter, that is open circuit voltage. And if you see the expression of open circuit voltage, that is into thermal voltage logarithmic of IP plus I naught upon I naught. So if you see this expression, you can say that open circuit voltage varies logarithmically with the incident solar power. Now coming to this second slide, in that if we see the effect of temperature on PV cell characteristics, then we can say that short circuit current ISC is a positive temperature coefficient. That means that ISC varies linearly as temperature goes up, or it declines as temperature goes down. And open circuit voltage having the negative temperature coefficient, it means that VOC is inversely proportional to the temperature. As you can see here, this VOC goes down as temperature goes up. And since we know that this power expression is equal to VI, therefore we can also say that maximum power is having negative temperature coefficient, and this maximum power goes down as temperature goes up, and vice versa. These are the temperature coefficient for this short circuit current, open circuit voltage, and this maximum power. So here, this T degrees Celsius denote that this short circuit current at the ambient temperature or the standard temperature that has been specified in the problem. And based on that, you can find, and by knowing this temperature coefficient, you can find the short circuit current, open circuit voltage at certain temperature, or this maximum power also. And this is the expression. We all know that this how to convert the temperature from Celsius to Kelvin and vice versa. Now coming to this efficiency calculation. So the efficiency calculation expression is, it is the output power upon input power, and the output power, the maximum output power that can a solar PV can deliver is that at MPP. So it is VMP into IMP upon this input power is the, if it is ideal case, input power is the area of cell into the insulation. So this efficiency you can find from this expression, where this VMP the maximum power point voltage, IMP the maximum power point current, and A cell denotes this cross-section area of this cell, and L is the insulation. And if you see the efficiency of a solar PV module, that is always less than the efficiency of a single cell. That is because this module area also includes the gaps and cases along with these pure cell areas. So these are not contributing any power generation through the module. That's why this efficiency of solar PV module is less than efficiency of solar PV cell. And efficiency of solar cell goes down as temperature goes up. That's because this peak power PM decreases with the increasing temperature that we have seen in the previous slide. Now the another expression that we are going to use in today's class, that is fill factor, and fill factor is denoted by this VMP into IMP upon VSC into ISC. So this is the first question of today's tutorial session. So before we begin to solve this problem, if you have any doubt, anything you need to ask, you can ask me. So we have 20 people in this meeting. So when I am solving this problem, you also need to give your answer in the chat box, or you can speak also. Yes, the video is available on YouTube, and I will also provide the link. So can any I also want to know that is your what is your in which course you are enrolled, or why you have taken this course. Can anyone tell? You can introduce yourself. You can tell your name and your college and your degree. Hello, yes, Prabhakar.
Yes, Mr. Gaurav. Myself, I am Prabhakar. Okay, I had registered this course as a part of my PhD coursework. Um, Actually, I had
Okay.
done this course in 2018, but again, I need to register due to this coursework. And the one reason I observed at that time to this one is in 2018 is the first time they had taken the course. At that time, the assignments are somewhat easy compared to this time and at the depth level. um, that's it.
Okay, okay. Actually,
Uh,
there is problem in my mic also. Your voice is not clearly audible to me.
okay, then I
Okay,
will
no
type.
problem.
Okay.
Yeah, yeah, it's okay.
Right.
My voice is clear or it is interrupting?
Now it is clear from your end.
Okay, okay, thank you. Okay, let's start today's problem. And whoever is getting the answer, you can type your answer in the chat box. So the first problem is that in photovoltaic cell characteristics, the slope of a constant current region and the slope of a constant voltage region imply F. And the options are series resistor, shunt resistor respectively, and B shunt resistor respectively, and C option is series resistor respectively, and D option is shunt resistor, series resistor respectively. You can give your answer in chat box. Yes, correct. So Vivek, Aditya Verma, Prabhakar, and Prabhakaran, Saurabh, Ravinandan, all of prepared Chandni, Hemant, Gumti Kalyani. So, so we know that this, if we see the IV characteristics of solar PV, then these shunt resistors, this high value of shunt resistor comes in parallel with this solar PV module. In the model of solar PV. So this so the for constant current region, the slope of constant current comes due to this shunt resistor, and for this voltage and the slope of a constant voltage region comes due to this series resistor. So D is the correct option. I think there are 5 to 6 questions are just oral type. We don't need to solve. And then after that, we will solve some numerical type problems. So let us see the second problem. The efficiency of a photovoltaic cell is fill in the blanks, then the efficiency of a PV module. Okay, Mayor Kager. Okay. So if you see IV solar PV module, there is something like this. So this is short circuit current, and this is open circuit voltage. So if you see this, this is not this straight line. So why this the bend happens? And if you refer this model of solar PV, equivalent circuit of solar PV, then from there you can this comes due to this shunt resistor in the short circuit current. And here in this voltage, this slope of constant voltage region comes due to this series resistor. Hello, yes. Can you type your can you type your theory so that I can give the answer? I think someone mic is on. Can you please turn it off? Hello. I think someone mic is turned on. Can you please turn it off? Yes. Okay. Why shunt resistor is usually for constant current? So you can refer this class lectures for the detailed analysis. So let us come to the next problem. So the efficiency of a photovoltaic cell is fill in the blanks than the efficiency of PV module. Yes, correct. Many of you have given the correct answer. That is the efficiency of photovoltaic cell is greater than the efficiency of a PV module. That we have seen in the introductory this quick recap slides. Because this solar PV module has whatever this area of solar PV module that not includes only this all this all photovoltaics, all the combination of photovoltaic cell. It includes these gaps and this gap between the solar PV cells. So this is the reason that efficiency of photovoltaic cell is greater than the efficiency of PV module. Now coming to the next problem, if the intensity of solar radiation increases on a PV cell, then short circuit current varies logarithmically and open circuit voltage varies linearly. And B option is short circuit current varies linearly and open circuit voltage varies logarithmically. And C option is short circuit current and open circuit voltage varies linearly. And D option is short circuit current and open circuit voltage varies logarithmically. It in chat box. Yes, correct. Correct answer is option B. The short circuit current varies linearly and open circuit voltage varies logarithmically. And we have seen the expression of this short circuit current that is approximately coming as this photo current and this open circuit voltage that includes this logarithmic scale. That's why this varies logarithmically with this solar insolation. Now, the next problem is that which is the correct relation of parameters with the temperature variation for PV cell. This is similar type of problem with the previous one, and the options are short circuit current varies inversely with the temperature, and B option is peak power remains constant with the temperature. C option is open circuit voltage varies proportionally with the temperature, and D option is peak power varies inversely with the temperature. Yes, correct. Hemant, Prabhakar, and also you all are correct. This D option is the correct answer. Peak power varies inversely with the temperature because it is having this negative temperature coefficient. Now the next problem is that calculate the fill factor of the PV cell with the IV characteristics shown below. So till now we have solved this verbal type problem. From now onwards, there is a mix of numerical and verbal type problem. So this is a numerical answer type. So in your exam also, some problems will having option and some problems you have to give the answer in the numerical type. So this is numerical type problem. There is some problem in my laptop also. Numerical type problem. So we know that fill factor is the ratio of maximum power coming through this solar PV cell upon this ideal case having ideal power, that ideal maximum power that solar PV can deliver, that is VOC into ISC. So from this figure, we can see that VOC is this point, and then short circuit current is this point, and then having maximum power point is this one, and then this is maximum power point voltage. So from this figure, we can say that maximum power point voltage is 6 and maximum power point current is 20 ampere. And then open circuit voltage of PV cell is 7.4 volt and short circuit current of PV cell is 31.5 ampere. So if you solve this, then it will become 120 upon 253.1. So it will give you 0.5148. So the range, the answer given for this problem is in the range. So the range is given as 0.4 to 0.6. So whatever the answer between these whoever types, then that will be considered as the correct answer. Yes. Prabhakaran ji, correct. False and Prabhakaran, correct. Harshit, what is the physical significance of fill factor? So here I will give you the means how to solve this problem. I think you all have gone through the class lectures, and from there you have understood what is the physical significance of fill factor. So I can give the answer, but not in a better way than whatever the class, whatever the professor has delivered. So here I will just the sample problems that will be similar to this assignment. I think many of you have doubts that are that have very deep meaning that professor can give the in better. I can give the answer not in that way. So if the fill factor of cell is more than the fill factor of module. So if you see this from my if in my understanding, if we are having PV module, then this that having series parallel combination of this PV cell, then this open circuit voltage comes as the comes as summation of its comes series combination of each PV series combination of the PV cells, and this short circuit current will having this uh, whatever the parallel strings that PV module has. So from there we get this open circuit voltage and short circuit current for that PV module. And based on the IP characteristics, we will get this maximum power point current and maximum power point voltage. So that is a very nice question. I think you can ask in this discussion forum whatever this analytical type of means doubt you have. You can ask in this discussion forum. So we will see uh, how we can give a good answer or better answer. Kriti, you have a very nice doubt, so you can ask in the discussion forum. So let us come to the next problem. That is question number 6. Referring to the data sheet given below, calculate the cell efficiency with an irradiance of 1 kilowatt per meter square in percentage. Nominal ambient temperature is 50 degrees Celsius. So we need to calculate the efficiency of this PV efficiency based on this data sheet given. So again, this is a numerical type problem, numerical type question. So we know that efficiency expression is the output power of solar PV cell upon the input power, and the maximum output power that solar PV can deliver is VMP into IMP upon input power will be this. Okay. So number of this solar cell in, and then area of each solar cell, and this insulation. Maximum power voltage that is given as 29.49 volt. So it is 29.49 volt, and this IMP is given as 7.80 ampere upon this number and type of cell. So here you can see this n is given as 60. And then area is given 156 cross 156 mm. So 156 cross 156 into 10 to the power minus 6 into L. Insulation, that standard insulation you have to take it, and it is given as 1 kilowatt per meter square. 1000 watt per meter square. So we have converted it into meter square, and here it is watt per meter square. So denominator will also in watt and numerator will also in watt. So it will be coming as 230 upon 1460 into 10 to the power 3. So it will give you, sorry, 10 to the power minus 3. So it will give you 0.1575, or in percentage will give you 15.75%. So correct answer for this problem is 15.75, and range is given for this problem is 15 to 16. Whatever the answer you type within this 15 and 16, then that will consider as the correct. Yes. Also Vivek, Prabhakaran, all of your correct. 15.75. Now coming to the next problem. So you need to calculate the short circuit current and open circuit voltage at 70 °C temperature using the temperature characteristics given below and the data sheet given in question 6. So based on the previous problem, here we have given this temperature coefficient for maximum power, open circuit voltage and short circuit current, and you need to find the short circuit current and open circuit voltage at 70 °C. So I will write here the open circuit voltage and short circuit current at the ambient temperature so that you can solve the problem. First is the current, short circuit current. So ISC from the data sheet, ISC at 25 °C is given as 8.39 ampere. 8.39 ampere. And this VOC at 25 °C is given as 37.20 volt. These two data is required from the data sheet to solve this problem. And here you have to calculate at 70 °C temperature. So let us start to solve the problem. So we know that temperature coefficient expression is denoted by alpha I, and it is given as change in ISC short circuit current upon ISC at ambient temperature 25 degrees Celsius into 100. So this will be numerator upon delta T. One mistake, one mistake here. So here this ambient temperature is given as, sorry, ambient temperature is given as 40 degrees Celsius, not 25. So generally we consider 25 degrees Celsius if nothing is given, but in the problem it is specified 40 degrees Celsius. So here you have to consider 40 degree. Sorry for this mistake. ISC at 40 degrees Celsius. Now this temperature coefficient for short circuit current is given as 0.053 percentage per degree Celsius. This one. So we have to put all the values here. So 0.053 equal to change in ISC. So we have to find the short circuit current at 70 degrees Celsius minus ISC at 40 degrees Celsius. That is 8.39 upon 8.39, and delta T will be 70 degree minus this 40 degrees. So it will come as 30 into 100. So from here we will get ISC at 70 degrees Celsius. So it will be 0.053 into 30 into 8.39 on 100 plus 8.39. So it will give you 0.1334 plus 8.39. So it will give you 8.52 ampere. So this is the answer for short circuit current at 70 degrees Celsius. So from this calculation, we have the two options B and D. Now we need to find this. We need to find this open circuit voltage at 70 degrees Celsius. And the temperature coefficient for open circuit voltage is minus 0.31 degrees Celsius. This one. This is negative temperature coefficient. So whatever the open circuit voltage at 40 degrees Celsius, so at 70 degrees Celsius, it is obvious that it is less than that. So from the option, you can see that this in D option, this is greater than given values, 37.20 volt. In the D option, it is given at 38.2 volt, and in B option, it is given at 33.74 volt. And since this open circuit voltage is having negative temperature coefficient, so the as the temperature goes up, this voltage will go down. So therefore, B should be the correct answer. So in either way, based on this, based on the idea of what is the meaning of positive temperature coefficient or negative temperature coefficient, you can opt the correct answer. And you can also find the find it numerically. We know that alpha V is the alpha V can written as change in VOC upon VOC at 40 degrees Celsius upon delta T into 100. So alpha V is given as minus 0.31 VOC 70 degrees Celsius minus 37.20 from 37.20 into 100 upon delta T will be 30. So VOC open circuit voltage at 70 degrees Celsius will be minus 0.31 into 30 into 37.20 from 100 minus 37.20. Sorry, plus 37.20. So it will be 33.74 volt. So B is the correct answer. If temperature coefficient, okay, how many returns? So if temperature coefficient in Kelvin, then it is to centigrade by taking temperature difference in centigrade. Yeah.
Actually, can I speak?
Yeah, speak.
Yeah, actually in the class, in the tutorial class, their sir has given in the data sheet mentioned alpha in kelvins and he has taken alpha as in kelvins and the temperature difference in the degree centigrade. Uh, is it correct way or else we need to convert that into degrees, alpha in degrees?
So yeah, here
Sir has not converted. He had taken alpha in Kelvin and delta T in centigrade, degree centigrade.
yeah, here the in the data it is given as per degree Celsius. So you don't need to convert.
Once
So
again.
yes, either way, means like this, we know that percent temperature in Kelvin, it is temperature in Celsius plus 273.15. So like here, if you see this delta T. So either you write delta T in Celsius or Kelvin, both having the same value. If you convert in Kelvin, then also delta T will be same. And if you are having data given in Celsius, then delta T will also be the same. The same value you get in the if you convert this in Kelvin. So delta T will remain same. Either you have calculate in Kelvin or you calculate in Celsius.
But alpha can I take in Kelvin and delta T in degree centigrade? Is it the correct process? Alpha in Kelvin and delta T in
Okay.
degree centigrade.
Okay. If alpha is again in Kelvin, then how we can proceed? So if you just convert this delta T on the basis of
No. I'm not asking that one. Sir has
Yeah.
solved an example problem. Sir has taken alpha as Kelvin, okay, and delta T as degree centigrade only. He has not transferred into kelvins there. Temperature has
Okay.
not transferred. Uh,
Okay. Okay. I got your point.
hmm.
Okay. So uh, if this alpha is given in Kelvin, but sir has computed this delta T in Celsius, right?
Ah, yes. Delta T in
Yeah. Yeah. So
centigrade and
as
alpha
I
in
told you,
Kelvin. Hmm.
so this delta T will it vary if you calculate in Kelvin or Celsius, because it varies with this it is added with 273 or subtracted, so it will get cancelled out. So delta T will remain unaffected. So it does not affect this calculation.
Okay, okay, sir.
Coming to the next problem, the next problem is that a photovoltaic module contains a 500 cell with a cell dimension of 100 mm cross 50 mm. If the module has efficiency of 18%, find find the amount of output power in watts that can be taken from the module. Assume irradiance L is equal to 1000 watt per meter square at 25 degrees Celsius. So this is simple problem. So we know the efficiency of photovoltaic module. The expression you can write the output power of PV module upon input power to the PV module. So output power we have to calculate. This efficiency is given as 18%, so it is 0.18, and output power you need to calculate, and input power, how you can write input power, you can having this n is denotes the number of solar cells and area of each solar cell, and this L is insulation. P out, and N is the number of solar cells, and area is given as 100 into 50. We have to convert into meter square, so into 10 to the power minus 6 meter square, and solar insulation is given as 1000 watt per meter square. So we will get P out as 450 watt. So the range for this problem is given as, if you type the answer in this range, then you will get the mass, that is 449 to 451. So the correct answer for this problem is 451. Yes, correct. Chandni and false. Will the value of alpha and degree Kelvin be equal? Please explain how. So I got so many questions, but I am honestly I am unable to give this answer correctly. So I will just write these questions this time, and I will give the answer in the next class. Sorry for this inconvenience, because there are so many analytical questions. I have to do analysis. If I say something wrong here, then it will be wrong impression. So the first problem that I got, the first doubt that I got, this one, this how this shunt resistance and series resistance that I have derived myself, but right now I am just unable to recapture, unable to get that point. So I will try to this and give the answer in the next class. Whatever doubts you are asking, the analytical doubts that I am not able to give the answer right now, I will give the in the next class before starting to solve the problem. I think that will be better. And the next doubt is that how this fill factor is varying if we are having the same solar PV cell is used for making the solar PV module. So that is also I will give the answer in the next class. And the physical significance that has been that has described by the sir. So you kindly refer the YouTube lecture video for this or for the class lecture. This professor has given the answer right away. So this question I will take care, and then this temperature coefficient in Kelvin or Celsius, it remains same or not. Yes, this calculation of shunt resistant value from the PV cell module. I think you are talking about the current assignment. I will see. So in the current assignment, I will just give you hint. Then if you make the equivalent circuit of PV cell, there we got this expression I light is equal to diode current plus shunt current and this PV current. And now for this short circuit current, this IP RS, this PV current into RS will become 0, and diode current with diode current is given as also 0 because it is negligible. So you can write this PV current is equal to this I light minus this shunt current. That is VPV upon RSS. And add this when this short circuit current and this you write the condition for this VPV that is equal to 0 for the short circuit condition. So you will get the expression of this PV current in the terms of slope. So I will give you hint here like this is the equivalent circuit of PV cell. PV, this is PV current and PV voltage. See IPV already reflected. And then this is shunt current. This is RSX. And then we are having this diode current, and this is photocurrent IP, or you can write I light. So you just write the expression for this. You can write apply the KCL here. This I light is equal to diode current plus this shunt current plus this PV current. And then this highlight, this PV current, you can write IPV equal to highlight minus ID minus VPV plus IPV RS upon RSS. So this is the mathematical expression for this equivalent circuit of PV cell, and based on the whatever the condition given in the problem, you can you can substitute and you will get one expression, and there you can compare with y is equal to mx plus c. So if you y in the y-axis we are having IPV and then m, and in x-axis we are having VPV, and you get some constant value. So this constant value like this. So see, like for if you calculate for this short circuit current, then C will come as ISC because it is intersecting this IV curve at this ISC. So this will be C will be ISC. And if you calculate for this open circuit voltage like slope for this one, then you will not get, it is having infinite value of this. It is not cutting this I axis, therefore you will not get the this C value, this intercept. We call it an intercept, where it is intersecting at the y axis, and this M we call it as slope. So you have to compare, and you have to compare this standard equation of a straight line y equal to mx plus c, and you will get the slope based on the condition provided in the problem. And if you are calculating the slope when considering this straight line, then you will get intercept at short circuit current ISC, and when you are calculating the short circuit, when you are calculating the slope for this straight line that is having open circuit voltage, this constant voltage region, then you will not get intercepts because it is having infinite value, because it is not cutting this cutting this y axis, that is I axis. Y just give you hint. Based on that, you can calculate the slope for this both the regions, this constant current region and constant voltage region. Yes, I will share this PPT also. No problem. I will share the PPT and this today recording lecture. Today this tutorial session recording. So whatever the doubt you are having that I am not able to provide, I will give the answer in the next tutorial. So coming to this tutorial session, so let us come to the next problem. So this is a very simple problem. The photovoltaic effect was discovered by, and the options are Albert Einstein, Adams and Day, and Edmund Wekler, and this Fritz CE. So which is the correct answer? Edmund is the correct answer. Jira, Chandni, Sarvan, Prabhakaran, all of you are correct. Very good. So, so this is the C option is correct answer. Now coming to the next problem. The next problem is that solar irradiance L equal to 1000 watt per meter square for 25 degrees Celsius. Open circuit voltage equal to 44.85 volt and open circuit temperature coefficient is minus 0.31 percentage per degree Celsius. Compute the open circuit voltage in volt with a live operating temperature of 315.15 Kelvin. So this is we have solved this type of problem. So we can start to solve this problem. So here this alpha V is given as minus 0.31 percentage per degree Celsius. And we are given this temperature in Kelvin. So it's better to convert this temperature in Celsius. So temperature in Celsius will be 315.15 minus 273.273.15. That will give you 42 degrees Celsius. So alpha V will be change in VOC. We know that alpha V expression change in open circuit voltage upon VOC at ambient temperature at 25 degrees Celsius upon delta T into 100. So alpha V is given as minus 0.31 change in VOC. VOC at 42 degrees Celsius. We have to find, and then VOC at 20, 25 degrees Celsius is given as 44.85. So 34.85. So delta T will give you 42 minus 25. So on substituting all these values, you can find open circuit voltage at 42 degrees Celsius. So it will be 44.85 minus 0.3117 into 34.85 upon 100. So it will be 44.85 minus 2.36. 2.3636. So it will be 42.486 volt. And the range for this range for this problem is given as 41.7 to 42.7. So we are getting answer as 42.48 volt. You are having the correct answer. Let me see. Yes. Prabhakaran, Vivek, Chandni, Prabhakar, Ajira, all of you are correct. So let us come to the next problem. Here it is given that consider a 36 volt battery with a 20 ohm series resistance. This battery resistance combination is required to emulate a PV cell. The fill factor is. So you have to find the fill factor. So to find the fill factor, we have to find the maximum power. So how we can find the maximum power if we are having this given with a battery and 20 ohm series resistance? So the maximum power transfer occurs when the load resistance equals to the series resistance. Equal to the source resistance or series resistance. Equals to the source resistance. So you can write R load equal to RS equal to 20 ohm. Now then the voltage will become half across each resistor. Then you can say that the voltage across each resistor will be half of the open circuit voltage. Therefore, then you will get VMP equal to open circuit voltage upon 2. So you can also write based on this data that this open circuit voltage is 36 volt and short circuit current will be, if you at the end of this battery, if we short circuited, then the short circuit current will be 36 volt upon 20 ohm. It will give you 1.8 ampere. So this we got from the data provided in the program, that is battery voltage and its series resistance. Now we have to find this maximum power point voltage. So maximum power point voltage will acting at VMP equal to VOC upon 2. So we will get this 18 volt. Therefore, IMP will be VMP upon R load, or you can write RS also, both are same. So VMP is 18 volt, R load is 20, then it is coming at 0.9 ampere. Now we know that fill factor is VMP into IMP upon VOC into ISC. So VMP is 18 into 0.9 and VOC is 36 into 1.8. So we get 1.4. Fill factor will come as 0.25. So fill factor is 0.25. So the correct answer for this problem is 0.25. Yes, Prabhakar, Vivek, all of you are correct. Coming to the next problem, that is question number 12. So in this problem, a PV panel delivers maximum power of 1 kilowatt at 200 volt. The efficiency of the panel is 20%, assuming a standard conditions. The area of the PV panel used is, you have to give the answer in square meters. So what are the data given? Given data are maximum power PMC, it is given as 1 kilowatt, and this VMP is given as 200 volt. Then we are given with efficiency, it is given as 0.2 or 20%. So we know that efficiency equal to P out maximum power upon input power. So we substitute all these values. Efficiency 0.2, P out will be P out, that is PMP only. So PMP is given as 1000 watt upon input power. Input power is area into L. Let me write one more line. Efficiency equal to PMP upon input power is area into L. Substitute all this value. 0.2 PMP is 1000 watt. We have to find the area and a standard conditions. It is given that you have to assume a standard condition. So standard insulation is given as 1000 watt per meter square. So area will come as 1 upon 0.2. So it will give you 5 meter square. The correct answer is 5. Yes, Vivek, also you are correct. 5 is the correct answer. Now come to the next problem. So here in this problem, a customer needs PV panel to supply an illumination load of 200 watt, he goes to a shop where the seller displayed two PV panels, PV1 and PV2. The two PV panels have the following specifications. And the PV1 is having the number of cells 100, dimension of each cell is equal to 10 centimeter into 10 centimeter, cell efficiency is 15%. And for PV2, number of cells is 75, dimension of each cell is 20 centimeter into 20 centimeter, and cell efficiency is 12%. Which PV panel is suitable for the customer? Assuming a standard incident solar power of 1 kilowatt per meter square. And here four options are given. Single option is correct. So what you need to do here, you have given this load of 200 watt, right? So based on the load, there are two PV panels available, and first you have to calculate this output power of PV panels. And if this output power of PV panels is greater than required power, then you have to opt that PV panels. If it is less than the required load, then you will neglect that. So you have to choose that PV panel whose output power is coming as the demand is coming more than the demand power. And the demand power is given is 200 watt. So let us see the first case, the case one. Case one, PV1. So here we are going to find this output power. Output power is efficiency into area into insulation. So efficiency of first solar cell is given as 15 and area is given as 10 centimeter into 10 centimeter. So it will be 10 to the power minus 4 meters square. And insulation is given as 1000 watt per meter square. So if you do the calculation, sorry, here efficiency you have to take it as 0.15, and the number of cells you have to also consider. So here you write in the number of cells in each PV panel. In each PV panel that is denoted by PV1, it is 100. So it will give you the output power is 150 watt. Now case 2, in that we are that is denoted as PV2. So output power for this type of panel is efficiency into area into L into the number of cells. Efficiency is 12%, so 0.12. Area is 20 centimeter into 20 centimeter square, so it will be 10 to the power minus 4 meter square, and L is 1000, and it should be multiplied by number of cells, so it is 75. Therefore Therefore, it will be coming as 360 watt. So this, don't confuse with this expression. We have used this expression one. This efficiency is equal to P out upon P in. So P out upon P in. So P out will be, so P in, how you can write, number of cells into area into L. So this expression we have only used. So now the demand power is 200 watt. And this for PV1, the PV1, the maximum power that can deliver is only 150 watt. And for this PV2, the maximum power this can deliver is 360 watt. So this is greater than demand power. So we have to take the second one, that only PV2. So the correct answer is B, only PV2. So the peak power delivered by PV1 is less than the required power for the illumination load and hence not suitable. And the peak power delivered by PV2 is greater than the required power for the illumination load. So it is suitable for the customer. So you can write peak power of PV2 360 watt is greater than the required power. That is 200 watt. Hence, PV2 is suitable. Yes, Prabhakaran and false, both of you are correct. Chandni, Vivek is Jira, all of you are correct. Now coming to the next problem. So the next problem that a PV panel measures open circuit voltages of 50 volt and 47 volt at 25 degrees Celsius and 45 degrees Celsius respectively. The approximate temperature coefficient of VOC is the percentage per degree Celsius. So we all know that this is a very simple problem. We have solved the similar type problem so many times here. So it is, we know that temperature coefficient for open circuit voltage is change in VOC upon VOC at 25 degrees Celsius into 100 upon delta T. So alpha V will be, change in VOC will be 47 minus 50 and VOC at 25 degrees Celsius is 50 volt and delta T will be 20 into 100. So in the numerator it will be minus 3 upon 15 to 20 into 100. So it will give you minus 0.3 percentage per degree Celsius. So the correct answer is minus 0.3. Clear, any doubt you can ask? Yes, minus 0.3 is correct. Chandni, this is around 0.3 because open circuit voltage having negative temperature coefficient. So if you should not do this common type mistake in the exam. Whatever mistakes you can do right now, and you don't need to do mistakes in the final exam. So the next problem we are having, a voltage source of voltage Vs is connected across the two terminals A and B of the resistance wire having length of 1 meter. The resistant wire having formed resistance of 100 ohm per centimeter. In this configuration, a sliding contact C is placed between the terminals A and B, from where an electrical connections can be probed. A PV panel in series with a galvanometer is connected across the sliding terminal C and the in terminal B of the resistance wire. The PV panel has an open circuit voltage of 40 volt at 25 degrees Celsius and 0.25 percentage per degree Celsius temperature coefficient of VOC. At 25 degrees Celsius, the galvanometer shows non-deflection when the sliding contact C is at a distance of 40 centimeter from terminal B. The approximate temperature of the PV panel for the sliding contact would show non-deflection from the galvanometer at a distance of 37 centimeter from the in terminal B is. So this is just only, it seems like very long problem, but it's not a very difficult problem. So we are having this voltage source connected across the terminals A and B of resistance wire. So this is, and make it as dark. So this is the resistance. So take it as A and take it as B. Now the resistance wire has an uniform resistance of 100 ohm per centimeter. So this is 100 ohm per centimeter. In this configuration, a sliding contact C. So a sliding contact C is placed between terminals A and B, from where the electrical connection can be probed. And a PV panel series with a kilometer connected across this sliding terminal C at the end of terminal B. So a PV panel is connected instead with the galvanometer across the sliding terminal C at the end of terminal B of the resistance wire. The PV panel has open circuit voltage of 40 degrees Celsius at 25 degrees Celsius. So it is given as VOC at 25 degrees Celsius equal to 40 volt, and this alpha B is given as 0.25 percentage per degree Celsius. At 25 degrees Celsius, the galvanometer shows non-deflection when the sliding contact is a distance of 40 centimeters from the terminal B. So when this galvanometer shows the non-deflection, for the galvanometer to show null deflection, this reference circuit voltage of PV should be equal to this voltage across CB terminal. So the first case, like it is given in the first case at the rate 25 degrees Celsius. So VCV 25 degrees Celsius, because it is showing null deflection at this point. So RCB from RAB into VAB. So how you can write the VCB? So it is RCB upon RAB into VAB. So it is simple. This comes from the voltage division rule. So VCB at 25 degrees Celsius is given as 40 volt. So RCB is given as 4 kilo ohm because this is given as 40 centimeter here. When a sliding contact is a distance of 40 centimeter from terminal B. So if this sliding terminal is 40 centimeter, that means that 100 ohm per centimeter into 40 centimeter. So it will give you 4 kilo ohm. So RCB is given as 4 kilo ohm, and the whole resistance of the wire is given as, since the length is 1 meter and 100 ohm per centimeter. So it will be resistance of RAB that is 100 centimeter. So it is 100 ohm per centimeter into 100 centimeter. So it will give you 10 kilo ohm. So 10 kilo ohm into VAB. So you will get the VAB voltage, or we can say the source voltage. It is coming as 100 volt. Now you have to find the temperature at which this P panel will show non-deflection. The galvanometer will show non-deflection, and you have to find the temperature for the P panel. So how we will use this data from the case 1. So in the case 2, at the rate T degrees Celsius, so we have to find VCB at T degrees Celsius, and this it is showing null deflection when this galvanometer and this C probe, this sliding contact is at a distance of 37 centimeters from the internal B. So RCB, RAB into VAB. So 30 cent RCB value will be 30 cent at 37 centimeter will be 37 centimeter cross into 100 ohm per centimeter. So it will be 3.7 kilo ohm. So RCB will be 3.7 kilo ohm, and RAB will be 10 kilo ohm into 100. So VCB at T degree Celsius will be 37 volt. So we know this VCB at T is 37 volt. Now we will use this temperature coefficient for the open circuit voltage. We know that alpha V is change in VOC upon VOC at 25 degrees Celsius upon delta T into 100. Alpha V is 37 minus 40 upon VOC at 25 is 40. Delta T will be T minus 25. At the top, it will be multiplied with 500. So alpha V is given as minus 0.25 into T minus 25 minus 3 upon 40 into 100. On solving this, you will get T equal to 55 degrees Celsius. So the correct answer for this problem is 55 degrees Celsius. And the range for this problem is given as 54 to 56. So this is a new type problem. Now coming to the next problem. A PV cell that measures 156 cross 156 mm can produce a maximum power of 1.3 watt at a solar insolation of 1800 watt per meter square and at a temperature of 25 degrees Celsius. Calculate the cell efficiency in percentage under solar insolation of 800 watt per meter square and the temperature of 45 degrees Celsius. Consider temperature coefficient of maximum power is minus 0.47 percentage per degree Celsius. So we have solved this type of problem so many times. So here you have to calculate the cell efficiency. And to calculate the cell efficiency, we need to first find the maximum power at 45 degrees Celsius. Because these data are given at 25 degrees Celsius. Area of PV cell, we can write 156 into 156 mm square. So converting to meter square, so we know that alpha P is change in PM upon PM at 25 degrees Celsius upon delta T into 100. So alpha P given as minus 0.47 percentage per degree Celsius. PM at 45 degrees Celsius minus PM at 25 degrees Celsius is 3.2 watt upon 3.2 watt and delta T will be 20. So given data you are having this PM at maximum power at 25 degrees Celsius is 3.2 watt and you need to find this maximum power at 45 degrees Celsius. And this alpha V is also given minus 0.47 percentage per degree Celsius. So PM at 45 degrees Celsius will be 3.2 minus 0.47 into 20 into 3.2 upon 100. So PM at 45 degrees Celsius will be 3.2 minus 0.3. So it is coming at 0.899 watt. Now we have calculated maximum power for this solar PV cell at 45 degrees Celsius is 2.899 watt. Now we can calculate the efficiency. So first for that we will calculate input power for the PV cell. Input power to the PV cell will be area into insulation. So area is 0.156. 0.156 insulation is given as 800 watt per meter square. So it will give you 19.4688 watt. Therefore, efficiency will be P out upon P in. So P out, that maximum power is coming at 2.899 upon 19.4688. So it will give you, if you multiply it with 100, it will give the answer in percentage. So the answer will coming as 14.89%. So the answer for this problem range given as 14 to 15%. Yes, correct. Ajira, you are correct. Very good. I think only you are solving right now problem. Now coming to the next problem. A, so, a solar PV cell is supplying its maximum power to a load at a constant load terminal voltage of 20 volt. The open circuit voltage of PV cell is 30 volt and short circuit current of the cell is 8 ampere. Fill factor of the PV cell is 60%. What is the load current in ampere? So, so here we have to find the load current. So all the data are given. We know that fill factor is expression VMP into IMP upon VOC into ISC. Fill factor is given as 0.6 and VMP given by 20 volts. So maximum power to a load at constant terminal voltage of 20 volt. So VMP is given as 20 volt and we have to calculate this IMP and VOC is given as 30 volt and short circuit current is given as 8 ampere. So IMP will come as 7.2 ampere. Now let us see the next problem. And the range for this problem is answer for the range for the answer is given for this problem 17 is 7.1 to 7.3 ampere. Yes, Chandni, Ajira, both of you are correct. 7.2 ampere is correct answer. Now let us see the next problem. In an ideal silicon-based solar cell is tested with a short circuit current ISC of 1 ampere at a solar insulation of 1 kilowatt per meter square at 25 degrees Celsius. What will be the open circuit voltage of solar cell at the solar insulation of 1.2 kilowatt per meter square at 25 degrees Celsius? Consider this I naught 7.5 milliampere, shunt resistance is very high and series resistance is very low, assuming volt equivalent temperature is 0.026 volt and diode ideality factor is given as 2, round of the answer to 2 decimal points. So we have to find the open circuit voltage at the solar insulation of 1.2 kilowatt per meter square and at 25 degrees Celsius. So we know that this photo generated current we know that this photo generated current that is IP. We also call it as photo current, photo generated current. IP is proportional to solar insolation L. IP directly proportional to solar insolation area. So when we are having this, and we also know this short circuit current is approximately equal to IP. Therefore, for the first case, when this insulation is 1 kilowatt per meter square, so IP1 is equal to 1 ampere. We can write because IS is given as 1 ampere. So at solar insulation of at solar insulation of 1 kilowatt per meter square. Now, how we can find IP2? We use this expression. So we can write IP1 upon IP2 equal to L1 upon L2. Why we are using finding this IP? Because in the expression of open circuit voltage, this photocurrent comes. So we have to find this photocurrent first. So IP1 we know that it is 1 ampere. IP2 that is solar insulation at 1.2 kilowatt per meter square. So you can write here IP2 equal to watt at solar insulation of 1.2 kilowatt per meter square. So L1 is given as 1 kilowatt per meter square and L2 is given as 1.2 kilowatt per meter square. So from here we get IP2 as 1.2 ampere. Now other things we know. So we know that open circuit voltage of PV cell is diode identity factor into thermal voltage into ln IP2 plus I naught upon I naught. This is the open circuit voltage of PV cell. Other things are known. This reverse saturation current, it is known 7.5 milliampere. So we have to substitute all this value and we will get the answer. Diode identity factor is given as 2. Generally for silicon it is 1 and for germanium it is 2. And weight is given as 0.026 volt. Ln, we have found this IP2. IP2 is 1.0 ampere and I naught is 7.5 milliampere. Seven point five milliampere. So open circuit voltage will be 0.052 ln into 161. So it will be coming at 0.26 volt 264 volt. So this is the answer. And the range for the answer is given as 0.25 volt to 0.27 volt. In this problem, it is a nice problem. It is a different type problem. And how many of you are solving? I think no one has given the answer. No problem anyway. So we have very less time. So quickly we will solve problem. Now coming to the next problem. As the incidence, so insulation on a PV cell increases, and the options are this one. I think we have solved this type of problem. Both short circuit current and open circuit voltage varies increase linearly. Open circuit voltage increases logarithmically. Short circuit current increases logarithmically. Both short circuit and open circuit voltage increase logarithmically, and open circuit voltage increases linearly. Just to give your answer in chat box. We have solved this type problem. Yes, Chandni, B is the correct answer. This open circuit voltage increases logarithmically. So B is the correct answer. Now, next problem. We have solved this type of problem also. So here, a battery of 9 volt with a series resistance is used for stimulating PV cell. What is the peak power of PV cell if internal resistance of the battery is 1? So here this series resistance and internal resistance both are given. And the previous problem, this internal resistance is given only. So we can write open circuit voltage is 9 volt, and this short circuit current we will find 9 upon 6. So it will give you 1.5 ampere, and maximum power point voltage will be VOC upon 2. How we are getting this VSC upon 2? We have derived in the previous problem. So from there you can easily get the idea. So you will get 4.5 volt, and this IMP will be 4. IMP will be this ISC upon 2. So it will be 0.75 ampere. So the peak power of the cell will be VMP into IMP. So 4.5 into 0.75. So it is 3.375 watt. This is the answer. And the range is given as 3.3 to 3.2. So how we are getting this IMP is equal to ISC upon 2? Because this resistance, this you can having this 6 ohms. So whatever the series resistance you are having, the load resistance will be same. So infinite load resistance will also 6 ohm. Because, and if you are just short circuiting, if you are doing short circuit, then and now this is IMP. So from here you get IMP equal to ISC upon 2, because it is voltage division. If you are doing short circuit, then all the current will flow only through this 6 ohm, and when in the maximum power point condition, this R load will come. So this will get divided. So IMP will be ISC upon 2. Who is asking this problem? Chidambaram, are you able to get it? Okay. Now let us come to the next problem. As I have made this diagram, so it will complete it. So this is 9. Now coming to the next problem. As the temperature increases, the efficiency of PV cell will improve, decrease, increase, remain unchanged. Give your books. Chandni, are you giving the answer for this problem number 21? So we know that efficiency of PV cell is PM upon P in, P out upon P in. So P out, we take it as the maximum power of the PV cell, and we know that PM is having negative temperature coefficient. So as temperature goes up, this denotes that maximum power will get down. So as the temperature increases, this PM will get down, and then then correspondingly this efficiency will also get down. So therefore, B is the correct answer. As the temperature increases, the efficiency of PV cell will decrease. Yes, Ajira, you are correct. Kalyani, you are correct. Now come to the next problem. As the incident insulation on a PV cell increases, the same type problem. Just read it carefully and give your answer. I think it is repeated one. By mistake, it got repeated. So for this problem, this open circuit voltage increases logarithmically. So B is the correct answer. It is incorrect. Short circuit vary linearly, increases linearly, and this open circuit voltage increases logarithmically. So B is the correct answer. Now come to the next problem. As the temperature increases, the peak power of PV cell. What is the effect on peak power of PV cell, short circuit current, and open circuit voltage? So peak power of PV cell decreases. That is having negative temperature coefficient. Therefore, A is the correct answer. Now comes the next problem. As the temperature increases, this open circuit voltage increases. Wrong. This is having negative temperature coefficient, so it will decrease. The peak power of PV cell increases. Wrong. As it is having negative temperature coefficient, the short circuit current value decreases. It is also wrong because it is having positive temperature coefficient. Therefore, D is the correct answer. Short circuit current value increases. Now coming to the next problem. Consider a 12-volt battery with a 10 ohm series resistance. This battery resistance combination is required to emulate a PV cell. The fill factor is. So the similar type problem. So the fill factor you can directly give the answer as 0.25. But if you want to get derive it, it is very simple. VOC is 12 volt. ISC will be 12 volt upon 10 ohm. So it is 1.2 amperes. So for PM, we know that this R load is equal to series resistance RS. So it is 10 ohm. So VMP will be VOC upon 2. So it is 12 volt upon 2, so it is 6 volt. And current at this point will be AMP upon RS, so 6 volt upon 10 ohm, so it is 0.6 amperes. Therefore, PM is VMP into IMP, so it is 6 volt into 0.6 ampere, it is 0.6 watt. So field factor will be PM upon VOC into ISC. PM is 3.6 volts, 3.6 watt. So VOC is 12 volt into 1.2 ampere. So it is 0.25. Now coming to the next problem, consider a 24 volt battery with a 10 ohm series resistance. This battery system combination is required to emulate the peak power that can be delivered. So we can directly write this peak power condition. You know that VMP will be VOC upon 2. So VOC will be 24 volt upon 2, it is 12 volt. And this IMP will be ISC upon 2. So ISC will be VMP upon this R load. So it is 1.2 ampere upon 2. So it is 0.6. So I did one mistake. ISC will be how much? 24 upon 10. So it is 2.4 ampere upon 2. So it is 1.2 ampere. Therefore, PM will be 12 volt into 1.2 ampere. So it is 14.4 watt. So C option is correct. And again, in this case, field factor is always coming as 0.25. You can calculate. Now coming to the next problem, photovoltaic cells are sensitive to. Options are infrared portion of solar spectrum, visible light portion of solar spectrum, ultraviolet light portion of solar spectrum, RF portion of the solar spectrum. So we are left with just few questions. You can quickly write answer. Why we are comparing battery with solar PV cell? Is there any similarity in characteristics? So here we are using the maximum power point theorem. How this type of problem, many times this type of problem asked in this examination. So we are having this solving this type of problem. So it's already time. So quickly give this answer. Photovoltaic cells are sensitive to. Can we treat PV cell as battery? No, we cannot treat PV cell as battery. PV cell has very entire different electric. If you see the equivalent electrical circuit diagram, it is very different from the battery equivalent circuit diagram. We cannot treat PV cell as the battery. Here for field factor, we are using this battery equivalent model because in that also we are getting VMP. We can find this maximum power point voltage and this open circuit voltage and short circuit current. Battery, is it CC or CV? Constant. These are charging modes. How will I don't think this you can treat this as battery. So for this problem, the correct answer is visible light portion of solar spectrum. Now let us see the next problem. A PV panel having an area of 1.5 meters square gives the following readings under standard test conditions. The short circuit current is 8 ampere. The open circuit voltage of 14 volt. The voltage at peak power is 36.5 volt and the current at peak power is 7 ampere. the field factor of PV panel is found to 0.7 to the efficiency of panel is. The maximum power we can find first VMP into IMP. VMP is given as this voltage at peak power at 6.5 volt, and IMP is given as 7 ampere. So you will get it as 255.5 watt. Now, how we can find efficiency? PM from P in, it is 255.5 watt, and P in the area into insulation area is given as 1.5 meter square. Insulation is given as a standard test function is given, so you have to take it as 1000 watt per meter square. So you will get efficiency of 0.17 or 17%. So correct answer is A. Now, the incident into power of panel is 1800 watt, the area of the panel is, and this fill factor is given. So we have found this efficiency PM upon area and full L. So this is similar to previous problem. So efficiency we have got 0.14. No, sorry, this efficiency we have to find this from incident input power. So efficiency we can write PM as 255.5 and input power is 1800 watt. So we'll get 18.2%. There are so many ways you can find the solution for this problem. Since this is length into power is given 1800 watts, so you can directly write A into L. So 1800 watt area is A into 1000 watt per meter square. So you will get directly the answer 1.8 meter square. B is the correct answer. Otherwise, you can also find from the efficiency expression, but there is no need to use this. You can directly use this expression. Now coming to the next problem, what is the equivalent circuit of an ideal photovoltaic cell? So we know this equivalent circuit of ideal photovoltaic cell. What should be the answer? Equivalent circuit of ideal photovoltaic cell is the current source in parallel with the diode. D is the correct answer here. Now the next group, among the following, which is not a variant of photovoltaic cells. So these are the variant of photovoltaic cell thin film panels, monocrystalline panels, polycrystalline panels, and this is not a variant of photovoltaic cell molten carbonate panels. Which of the following is true about batteries? So these are general questions I have included from the previous assignments. So they are having higher energy density but lower power density. C option is correct. So this is having different characteristics from the supercapacitors. In supercapacitor, they are having higher power density but lesser energy density, which of the following is true. So this two voltage source can be connected in series. B is the correct answer. And two current source can be connected in parallel. A is the correct answer. And here inductor offers infinite impedance to the DC source. This is wrong. It offers zero impedance to DC source, while capacitor offers infinite impedance to DC source. So D is the correct answer. None of this. This is the last problem. Series diode are in P panel to blocking the reverse current. For today's session, so whatever the doubts you are all having, I will try to cover that. I will not able to give you today in today's session. Okay, you are saying this constant current source or constant voltage source. So we have to see this battery equivalent circuit. Any other doubt? Yes, I will provide the today's PPT, and I will provide the link also. Thank you all of you for attending this session, and we will meet on the next week at the same time. I hope you all are able to solve this current assignment number 1. Thank you all, and good night.